I'll call that C1. This part, all of this boundary except for a shared one I'll call C2. And then the boundary in between, call C3. Right. So now here's some important notation that you should be aware of. The boundary of D1, so you're actually using a partial differentiation symbol with D1. So anytime you have a region, if you put this in front of it, it refers to the boundary. So boundary of D1 is going to be C1, and we'll give C1 the proper orientation, counterclockwise, and then we'll give C3 this orientation so it's consistent. So C1 joined together with C3 gives you the boundary of D1. On the other hand, the boundary of D2, that's going to be C2, we'll give it the proper orientation. But now C3 needs to be given the opposite orientation to be the boundary of this region, because, yeah, you got to look to the left. So it's going to be union minus C3. Okay. So now if you want to apply Green's theorem to the entire thing, well, for the double integral side, double integral over D of qx minus py. Right. Well, the double integral over the entire region, that's just going to be the sum of the integral over D1 plus the integral over D2. All right. So, if Green's theorem is to hold, we should be able to express the line integral over the entire curve as the sum of the integral over this boundary and over this boundary. But some of those boundaries aren't quite the same. They have this shared piece in between. Fortunately, it turns out not to be a problem. Because if we actually write out what that is, so we'll use Green's theorem on each domain, D1 and D2. So now we have the integral over C1 plus integral over C3 all right, so all of this, that is equal to double integral over D1 plus integral over D2 plus the integral over minus C3 and all of this is equal to double integral over D2. Okay. Well, when you put these two together, these are going to cancel. Yay. Because we have C3 and minus C3. So the integrals over these are just going to cancel out. That's what's always going to happen when you have a shared boundary and you're keeping that counterclockwise orientation on each subdomain. So all you got left is this. So you get the integral over C1 plus integral over C2 is the integral over C pdx plus qdy. And because you've used Green's theorem on each subdomain, that is equal to that. So Green's theorem applies on the union of domains like this, and you can repeat this process to apply to any finite union of simple regions. So you can apply it a lot more broadly than what was first shown. And it all stems from the fact that the integrals over shared boundaries, these common walls, always are going to cancel.
So after they cancel, then you just adding the integral of C1 and C2.
Yeah, so just the actual exterior boundaries.
Okay, and then since you're adding those, you can say it's the one integral of those two.
Yeah, because what you're doing is you're applying Green's theorem to each piece individually, but on the double integral side, because you're talking about areas, you're just adding everything up. So you might think, well, okay, you can add everything up as far as double integrals over regions goes, because you're pasting regions together, but it's not immediately obvious that you can also do the same with the boundaries, but it's because of the cancellation that you actually can.
Right.
Yeah. So you end up not only assembling the regions together into one, you're assembling the boundaries together into one.
So that's our general formula. Right there.
Well, yeah, this is the process that lets you extend it to more general regions. So, yeah, Green's theorem is always going to be or really just, yeah, this whole thing. Okay.
All right.
In fact, the region doesn't even have to be simply connected. Even if it has a hole in it, Green's theorem still applies. And I can show pictorially why that would be. And it's rather similar reasoning. So let's suppose you have a region and it has a hole. Okay. So we give positive orientation to this part of the boundary, and then here, for a region to be on the left, we have to give it the opposite orientation.
Right.
And we'll call this C2. So now what you can do is, I'm going to cut this region into two regions that are simply connected. And now I can apply Green's theorem to this piece and this piece separately.
Well, that's okay.
And once again, the integrals over common boundaries are going to cancel. So what happens is, for this piece, we're going to go along here, this orientation. We go here, here, the top part, and keep going. And then for the bottom part, we use the bottom half of this boundary of the hole. And notice we've divvied up the boundary of the hole and of the entire region, but each place where portions of these curves are used, they always have the right orientation. So we're using positive orientation here and here. So again, we can just add the line integrals over all the boundaries that are not shared, and all of these will end up canceling. So it's the same argument as in the case where you had just two regions being pasted together. Yeah. Yeah. So what you would end up doing is the double integral over the entire region is going to be the integral over C1, just a line integral, and over C2. So you do need to count for all boundaries, and you need to make sure they're oriented correctly. And so you need one parameterization for this piece and a separate one for this piece, but then you can just add the results together. So as long as you're accounting for the entire boundary, Green's theorem still works. All right. So questions about how we handle this kind of region? All right. Well, if you ever half of the classes here, they might have questions.